Thank you. Yes, it is an absolute pleasure to be here tonight. And I've been wanting to come and give a talk at the RI for a long, long time. So this fulfills one of my ambitions in life. And I'm extra pleased to be able to come and talk about the book that I've been writing, 15 Million Degrees. So I'm going to talk about the book tonight, which means you don't have to buy it if you don't want to. I'm going to tell you what's in it. Sorry, Penguin. But what I want to do is convey, first of all, where we are with modern solar physics research. What are some of the interesting topics that we're focusing on at the moment? But then make the most of the fact that we are here in this very significant building, and this spot is very significant for scientific developments and the publicity and the public engagement around science too. So when I was writing this talk, I thought, right, I must go and have a rummage through the RI archives. So I did that, and I spent half a day looking through Michael Faraday's work and many other people's work, reading the Friday evening discourses that have been held here. And I would encourage you to do the same as well. You are all free and able to book an appointment and have a look through the archives, and it is an amazing thing to do. So some of the things I found out during that visit are in this talk. And I want to sort of convey a little bit about the history of science and then how we've got to where we are today and what that means for us in modern solar physics. So it's been a lot of fun writing this talk. It's been a lot of fun writing the book. But I also have an awful lot of fun doing the research too. And that's what I want to talk to you about really this evening. So when it comes to talking about the sun, I have to show photos, images that we take, particularly from spacecraft. And I always find it quite good to start off with these kind of images, which show the sun as we see it in visible light. So this is how our eyes see the sun, the wavelength of light that our eyes detect. And actually, this image is one that's been taken by NASA's Solar Dynamics Observatory. It's been in orbit now for just over 6 years, and it is the telescope or the suite of telescopes that give us the highest resolution images of the sun. So this is the visible light images. We see sunspots on the surface of the sun, which the number of which vary in time. So some of you may have heard about the solar cycle, where the number of sunspots rises and falls over a timescale of around 11 years. So this image, this is an old one now, actually from a few years ago. And we've just come through solar maximum, and we're on the declining phase of the cycle now. So we can look at the sun in visible light, see features on the visible surface. But I'm a space scientist. And so the view of the sun that I enjoy and that I use in my research is the view that we can only get by going above the Earth's atmosphere. And that means we can see all of the sun's radiation, from radio wavelengths all the way through to gamma ray radiation as well. But if we look in ultraviolet light, that's where I think we see some of the best views, some of the most attractive views of the sun. So if I was to show you the sun at exactly the same time as this image, but just using a different wavelength of light, it looks like this. Oh, excellent. I do love that response. I hope to get perhaps one or two more oohs out of you as the talk goes on. So this is the sun's million-degree atmosphere that we call the corona. You can see it has a completely different shape and structure to the photosphere that I showed you before with its dark sunspots. Now you see what looks much more three-dimensional. And that's because the light being given off from this layer, well, the light is coming from a layer that we call optically thin. So photons all through this gas can make it out and reach our telescopes. But what you're looking at here is light in the ultraviolet part of the spectrum, in the extreme ultraviolet part. So we can't detect this light from the surface of the Earth. We have to go into space. So we gather light across all of the wavelengths, but we don't just use the light to take images. I mean, my research focuses a lot on the images, but some of the instrumentation that we build at UCL uses the technique where you split the sun's light up into a rainbow. So in the sort of very basic sense, you might think about the prism, sunlight coming through a prism, perhaps as Newton did in the 1600s. The sunlight comes through, splits up into the rainbow. You could display that in a different way, and you could say, right, I'm going to have wavelength running along the horizontal axis, going from short wavelength blue light to long wavelength red light. You could even plot a graph to show you how much light you have at different wavelengths. So this might look something like you have on the screen now. So this is a plot, just a sort of schematic showing that you might have different amounts of light at different wavelengths or different colours. So what you're looking at here is something that we would call a continuum, which is a sort of curve. But then superimposed on that, you have what we call spectral lines. So in this case, dips in the amount of light, but they could also be spikes in the amount of light. So we would say absorption lines or emission lines, depending on whether light is being absorbed by gas in the sun's atmosphere or emitted by gas in the sun's atmosphere. So I just want to sort of introduce this as a technique that we can use to learn more about the sun. Looking at this particular part of sunlight, the visible light, gives us an idea of the surface temperature of the sun, which is around 6,000 Kelvin. But you can also use these spectral lines to probe what the sun is made of, because particular atoms of particular elements absorb and emit light at very distinct wavelengths or frequencies, depending on how you think about it. So these spectral lines can be really, really important. And one of the things that we do now is not just utilise the visible part of the spectrum, but also those other parts as well. So one of the instruments that we have in space at the moment that was developed by my department, the Mobile Space Science Laboratory, is flying on a Japanese mission called Hinode that was launched in 2006. And the kind of spectrum that this instrument takes looks like this. So this is now the sun's ultraviolet light, taken using a technique where you just take a narrow part of the sun's disk. So it's like looking through some shutters. The light comes through the shutters, gets dispersed, so that you can see all the different wavelengths. So if I was to then turn this into a graphical representation, into a plot, we'd have wavelength going along that horizontal axis again, and then the amount of light at different wavelengths that you see. And you see that it corresponds, those bright streaks, where we've got lots of light coming in at that wavelength, correspond to a nice spike in the spectrum. So here we have a series of spectral lines, emission lines, each one being formed by light emitted by particular atoms or particular ions in the atmosphere of the sun. So I could label these, I forget exactly what they are now, but they might be ions of iron or calcium or silicon and so on. So we can use them as a fingerprint to work out what's in the sun's atmosphere. But because this instrument is something called an imaging spectrometer, we can do even more than that. So I can take my slit of the instrument and move it slowly across the sun. And that means I can make images using my spectrometer. And I can make images at different wavelengths. And that's what you're seeing here. So these are images taken or created with our spectrometer on Hinode that show the sun's corona in different wavelengths of light. And those different wavelengths of light map to different plasma temperatures. So going from the coolest in the sort of middle bottom up to the hottest in the top left-hand side. And actually, one of the wavelengths that you see here is a particular emission line being given off by iron 12, you can see the Fe, and then the numerals iron 12, 195 angstroms, and that's the wavelength of light that I used to make the picture for the front cover of the book. So it's one of my favourite wavelengths of light that the sun gives off. It's quite sad. We sort of develop favourites, and 195 iron 12 is my favourite. So yeah. So I can gather spectra of the sun. I can make images, and I can also make movies. So I can run this over time, and you can see this particular region evolves. And actually, this is a region of plasma above a sunspot region on the sun. But even more than that, so this image that you're seeing now has blue and red patches in it. And so as well as using a spectrum to understand what elements are in the atmosphere of the sun, we can also look for things like plasma flows, because light becomes blue shifted when it moves towards you and red shifted when it moves away from you, the same as we experience with sound waves from a moving source. So having a spectrometer flying in space is incredibly versatile, and it allows us to do some really good physics about the atmosphere of the sun. But as I mentioned, I'm quite heavily reliant on images of the sun. And so I want to show you some of the activity that we detect once you start looking at a series of images put together. So if we go back to this view, this is the one I showed at the start of the sun's corona, looking at plasma that has a temperature of a few million Kelvin. And I can run a movie of this. But actually, what I want to show you is a movie that's been made by processing the data in a particular way. So this is the start of the movie, and it's the sun at exactly the same time. But this movie, which has been made by one of my colleagues, Dave Long, is using the fact that if you subtract one image from another, so you literally take your intensity across the image from one image to the next and do a subtraction. So any features in the sun's atmosphere that become brighter will appear as white. Any features in the sun's atmosphere that become less bright will darken. And things that don't change will remain grey. Now, this movie is slightly more complex because we've got 3 different wavelengths of light that we're using. So they're listed on the right-hand side in blue, green, and red. So we can do a little bit of a proxy about temperature changes in the atmosphere as well. But what I want to do is show you the movie, and hopefully you'll see dynamic activity revealed. So it flickers a bit as it's running before the main event happens, and you see a bright flash of light, and you see this huge eruption taking place in the sun's atmosphere. So this is a kind of activity, a form of activity that we call a coronal mass ejection. It's not the best phrase that we've ever come up with in solar physics, but it does what it says on the tin. It is an ejection of mass, of plasma, from the sun's corona, from the atmosphere. And these are this is the form of solar activity that I study in my research. So later on, I'll come back to how we think these things are being formed. And they are incredible. We can watch them flowing out into the solar system. So this is now the same event, but seen using a different kind of telescope. This is an instrument that creates an artificial solar eclipse. So it places a disk in front of the sun, blocks out the bright light of the photosphere, and leaves the atmosphere of the sun revealed by light that's actually scattered by the plasma. So this isn't direct emission that you're seeing here, but scattered light coming from photons that are deflected in this cloud of moving plasma. So this coronal mass ejection flows away from the sun. And it travels, I forget the speed of this one, but in general they can move between maybe a few hundred kilometers a second to maybe over 2,000 kilometers a second. And so they are fast. They carry the same mass as a mountain. So for those of you who remember your equations about kinetic energy, half mv squared, enormous amounts of energy. And it's been a big question in solar physics to try and understand where that energy comes from. So these are coronal mass ejections. And actually, incidentally, that black arm that you can see coming from the left-hand side of the image up towards the center, that's the arm that holds the occulting disk in place in our telescope. And this is a telescope that's... actually, this one's not orbiting the Earth. This one is orbiting a point called the first Lagrange point, which is a small fraction of the distance between the sun and the Earth. So if I have this movie and I run it again, but this time allow it to run for longer, you'll be able to see another effect come into play. So first of all, you'll see the eruption itself. Off it goes. And then as I run it further, you'll start to see these white flecks that appear in the image, and gradually a sort of snowstorm effect builds up. And it becomes completely dominant over the image to the point where you can barely see anything else. Now, these snowstorms are caused by electrically charged particles, protons, that are accelerated away from the sun at speeds close to the speed of light. They take, let me say how long the coronal mass ejection takes first of all. So I've already said that travels at 2,000 kilometers a second or more. And a coronal mass ejection takes perhaps 2 to 4 days to travel the 150 million kilometers between the sun and us. These particles, these protons, that get accelerated during these events take maybe half an hour to get to us. So they are incredibly fast. They hit our electronic detectors, they create a current, and that current is then registered by these bright specks. And actually these particle storms, we call them solar energetic particles, SEPs, again, another not particularly romantic name, but does what it says on the tin. These are the kind of events that if they happen whilst astronauts are doing spacewalks, can be incredibly hazardous. the Apollo astronauts reported having flashes of light in their eyes, even when they closed their eyes, and that was because of these high-energy particles coming in and interacting with their retina. But the more dangerous side is that if you get a storm of this ionizing radiation, you could end up with radiation sickness or leukemia, or perhaps even a fatal dose if it's really extreme. So the manned space program always looks at the sun to see what's happening so that they can forecast and get astronauts into a more shielded part of the space station should they need to. So coronal mass ejections and solar energetic particles. I just want to show you another coronal mass ejection, which is my favourite one that the sun has ever produced. And it's one that happened in June 2011. And I remember this clearly because I was at Cheltenham Science Festival at the time that these data were released. And I remember seeing the movie going around on the internet, and I didn't believe that it was real, actually. I thought someone had photoshopped it. So I went back to the NASA data archive, I got the data myself, and this is the movie that I made. So probably, if you haven't seen this movie before, you might not think the sun looks particularly special on this day in June 2011. I didn't. But there's a region on here that just did something phenomenal. So let me play the movie. So off it goes. I got a little ooh there. Yeah, good. So this remains for me the most spectacular eruption that the sun has ever produced. This time, so much plasma was thrown up against the huge gravitational pull of the sun, 27 times what we experience at the surface of the Earth. So much gets thrown up that a lot of it falls back down to the surface of the sun. And I know of many PhD projects who have carried out research on just this one eruption. So I have one student who's looking at it. So we want to understand what's driving these events. Where does the energy come from? So that's it as shown in ultraviolet light, looking at plasma that's around 80,000 Kelvin. But I can also do what I did before and show you this so-called difference movie to see just how much more detail gets brought out when you use this technique. So this again is a movie by my colleague Dave Long, and this is the same event. It's much better, isn't it? It looks amazing. I trained as an artist before I trained as a physicist, and actually I think there's something about these events that really appeals to me on an aesthetic level, that I just love to see these kind of data. So you can see this huge bubble that really rapidly expands, and then that material gets thrown up into the atmosphere of the sun. And these kind of difference movies are really useful to pick out the detail. You can see the downflowing plasma, you can see where it's crashing into the lower atmosphere, which is just a gas, it's not a solid surface. But as the gas gets compressed, it gets heated, and then it starts to glow again. So coronal mass ejections are scientifically fascinating, but also pretty beautiful to look at too. But there's one more form of solar activity that we're focusing on in solar physics at the moment, and that's something called a solar flare. And I've got another movie here. This is now taken from one of the Stereo spacecraft, which is a NASA mission. It's looking at the sun's atmosphere, again, the corona in extreme ultraviolet light. And when I play the movie this time, you'll see a flash of light happen in a region above the sunspots. So this is what we call a solar flare. And this is the form of solar activity that we've known about since 1859. A huge amount of work has gone into trying to explain, again, why these happen. When a solar flare occurs, you see a flash of light across the entire electromagnetic spectrum, from radio often into gamma rays, but certainly this intense brightening in ultraviolet light and also in X-rays as well. So solar flares are another big topic of study. This is another movie taken from the SOHO spacecraft, just showing what a solar flare can look like when it's directly along the Sun-Earth line. So in this case, sort of top middle of the sun, you see a solar flare go off. There's also a coronal mass ejection from exactly the same region at exactly the same time, but it's just hard to detect in these images. You need those artificial solar eclipse images to see it. And you have a solar energetic particle event. So we have coronal mass ejections, energetic particles, and flares happening often all at the same time. But perhaps one of the biggest discoveries about the space age has been to do with our relationship with the sun. And that's well illustrated by this animation. So this takes a bit of a setup, because what you're seeing here are images from two different spacecraft. And again, this is the NASA's stereo mission. You'll see I've pointed to the sun in the centre. So now the sun looks tiny. This is such a wide field of view that we're looking at. The sun is absolutely tiny. On the left-hand side of that image, you've got the view from one spacecraft, which has left the Earth, travelled away from us, and is now looking back along the Sun-Earth line. On the right-hand side, you've got the counterpart spacecraft, which has left the Earth, gone behind us in our orbit around the Sun, and is looking back along the Sun-Earth line. So these two spacecraft are looking at the same region of space, but from different directions. And now, if I run the movie, in fact, you can see the Earth. The Earth is in these images. That is us. We are seen by this spacecraft. So if I run the movie, you'll see immediately what I mean about our relationship with the sun. So you see a constant outflow. These coronal mass ejections, they flow out, they don't stop. They flow over the Earth. They flow over all the planets, the objects in the Kuiper belt, and they keep going until they reach the edge of what I would call the edge of the solar system, which is far beyond where the planets are orbiting. And not only do we have these coronal mass ejections, but actually because the sun is a hot, dense ball of plasma in the cold vacuum of space, it's actually got enough gas pressure in its atmosphere to overcome gravity, and the whole atmosphere at the top is expanding. And we call that the solar wind. So not only do we have eruptions, but we have a constant expansion of the sun's atmosphere that washes over all of us. The Earth is literally living in the atmosphere of the sun. We are living in the atmosphere of the sun. And it has some pretty big consequences for us. And so sort of maybe the impact side of the research that people like myself do is something that we call space weather. So there's a big push now, or a big drive to understand, okay, well, when these eruptions of plasma of the coronal mass ejections get to us, when the solar wind gets to us, when the energetic particles get to us, how do they deposit their energy in our magnetic field, in our atmosphere, in the surface of the Earth, and what impact does that have? So up here, I've just got listed some of the ways that these events can affect us. So coronal mass ejections in the past have caused disruptions or perhaps even outages to our electricity network. Solar flares can heat up the atmosphere, causing it to expand, causing problems with atmospheric drag on satellites. They deorbit more quickly. And energetic particles that I mentioned earlier are really hazardous for astronauts in particular, but there's also lots of work looking at, well, actually, if you're working in the aviation sector, what impact do these particles have on human health for people who are working on aircraft, but also for the miniature electronics on aircraft themselves. And so myself, my colleagues and scientists around the UK are all working on trying to understand what does this solar activity mean for our everyday lives. And very recently, the Met Office set up a space weather forecasting centre. So you can go to the Met Office to know whether you need your umbrella tomorrow, and Tim Peake can go to know whether he needs his, metal umbrella tomorrow as well. So there's a huge amount of investment, but for very good reason. So that was my kind of intro section to show some of the solar phenomena that we're focusing on to try and understand. And I'm going to come back to why or how we interpret them, what the physical processes are, in the last part of my talk. But for the middle part, I want to just say a few words about how far we've come. What has the story been to get to the point of being able to understand these events? And we have made a huge amount of progress. So I was sort of reflecting on, okay, I'm giving the talk here tonight at the RI. What's been that story since the RI was formed in 1799? And I think it's fair to say that we had fairly primitive views at that point. Now, the images that I'm showing here predate the formation of the RI. So on the left-hand side, I've got a drawing of the sun made by Thomas Harriot in 1610. This is the first drawing of the sun through a telescope, or the first drawing of sunspots even. And so you can see those dark patches that he saw as he looked at the sun. Foolishly looked at the sun through a telescope directly. Never do that. Really bad idea. And it's really nice when you read his notes. He talks about looking like quickly with his right eye, and then his left, and his right, and his left. You can see why. But luckily he did, and we have this amazing drawing which shows us that the sun has these spots on the surface. But of course, they're not discussed in his writing because there was no expectation, I suppose. What should the sun look like through a telescope, and are these features on the sun or not? That was a huge debate. But I like to show this because this is a British drawing, the first record of spots on the sun. The person who's more famously associated with sunspots is Galileo, and these are his drawing of sunspots from the summer of 1612. Amazing drawings. They show structure. They show that the sun is rotating. As long as you assume that spots are on the surface of the sun, which we know they are on the surface of the sun, so you can get the rotation rate of the sun just from something as simple as looking at the spots. So, in fact, everybody in this room could do this experiment. You can work out how quickly the sun rotates, and if it rotates at different speeds at different latitudes, because you can use the sunspots to be able to do that. So, when the RI was formed, we had, almost 200 years of sunspot observations, of sunspot drawings, but there was no idea about what they were. 200 years of work, and we still didn't know what they were. And that's because our ideas about light hadn't been developed enough. So the way the sun sends us information is in its sunlight. Everything that we know, what it's made of, how it's moving, is captured in its sunlight. I suppose that, and the fact that because we live in the sun's atmosphere, we can send spacecraft directly into it and measure the particles in situ. But before we had the space age, this was the way that we were able to study the light. And it's interesting reading back about the early stories of sunspots because they all drew on terrestrial experience. And I suppose that's quite natural. When you're trying to explain an alien concept, you draw on what you know. So there's discussions about sunspots being hurricanes in the sun's atmosphere or volcanoes on the sun. I quite like the work that was done by this chap. This is William Herschel. At the end of the 1700s, he was the person who had the best telescopes, and he was using them to look at the sun. But even he didn't know what the sun was and what sunspots are. But he has this really nice piece of reasoning that I was reading in one of his papers, so he's trying to figure out what the sun is, what sunspots are. And so he has this reasoning where he imagines an observer on the moon, and they're looking back at the Earth. And he thinks, well, what would they see? And so he thinks, well, actually, they could only see the surface of the Earth where there's gaps in the clouds to be able to see through. And then he thinks, well, actually, if they were looking at the night side of the Earth, they might see some glowing gases, the aurora. So glowing gases, glowing sun, okay? So there's glowing gases in the Earth's atmosphere. At this time, they had also made observations of other planets, of course. And one of them, observations of Venus, also showed glowing something on the night side of Venus. This is called the ashen light. So William Herschel was using terrestrial reasoning and his observations, amazing observations of the planets, to try and learn something around the sun. And he ended up concluding that a sort of planetary interpretation of the sun, where you have a glowing atmosphere, and the sunspots are these holes in the atmosphere, breaks in the hot glowing clouds where you can see down to the surface of the sun, the cool surface of the sun. And in his paper of 1795, he even has this line where he says, "This leads us on to suppose that it is most probably inhabited, the sun, like the rest of the planets." Lewis, is that true? By beings whose organs are adapted to the peculiar circumstances of that vast globe. So I think this says everything, that we really didn't have a clue. But today we do. So how did we get there? And that brings me on to the Royal Institution and the key player of the Royal Institution, which is Michael Faraday. Because what I want to talk about now is magnetic fields. It turns out that magnetic fields are centrally important to understanding the sun. And so that's what I'm going to focus on for the rest of my talk. So when I came here and I had a rummage through the archives, of course I wanted to see the work of Michael Faraday. And Charlotte New here very kindly showed me Michael Faraday's lab book. So this is one of them. This is his writing. And in this experiment, he's using a wire that he's passing a current through, and that's generating a magnetic field. So this is Ampere's law. You pass the current through the wire, and you have the circular magnetic field around your wire. But what I hadn't realised was how he had captured that magnetic field. And that's what's being shown here. So these are iron filings that he put down onto melted wax, so the wax would set, and in it would be captured the shapes and the strengths of the magnetic fields. Amazingly simple. Again, something that we could all in this room do. I just love the fact that this is so important, but so simple. And this is another one of the images or figures that he created. So again, you can literally see where the magnets were underneath the paper, and you can see the shapes in the iron filings. And this is classic school experiments investigating magnetic fields. At home, I have a pot of iron filings. It's so good. And so here you can see the shapes in the magnetic fields. And one of the things that I didn't realize for a long time is that when I talk about magnetic fields and I'm trying to convey them to a colleague, what I quite often do is draw a picture. So I would draw my magnet, my North Pole and my South Pole, and I would draw magnetic field lines in between the North and South Poles. And where those lines are bunched up, that means I have a strong magnetic field, and where they're spread out, I have a weak magnetic field. But I also put arrows on to go from north to south. So I use the concept of a magnetic field line just to show the shapes that these iron filings are tracing out. And what I hadn't realised was that this is a concept that Michael Faraday came up with to communicate about magnetic fields. And I just think it's so lovely that we still rely on it really heavily today. So at home, yes, I can be found with my iron filings, and at work I draw them, but I'm also a big fan of pipe cleaners. So with my students, we're always making shapes with pipe cleaners to show magnetic fields, or to help our discussions about magnetic fields. So Michael Faraday, huge amounts of work on electricity and magnetism, here in this building, on this spot, talking about them. I hope I'm doing him justice. And in 1845, Michael Faraday discovered a connection between light and magnetism, so that you can rotate the plane of polarization of light when it passes through a magnetic field. But one of the other things he was working towards was to use a spectroscope. So as I mentioned earlier, we use spectroscopes or spectrometers today to split light into its component colors and look at the spectral lines. And Michael Faraday was interested in, would there be any effect on a spectral line of a substance, of an emitting substance, if it were influenced by a magnetic field? Now, his apparatus wasn't good enough to answer that question, but it's something that got picked up again or continued to be worked on. And so my story now moves from Michael Faraday to some other people who were key players in bringing us from magnetic fields in the lab to magnetic fields, well, on the sun. So the next person in the story, which is heavily condensed, is Peter Zeeman. And he was also working on spectral lines and magnetic fields. And he was the person who showed that, yes, if you had an object emitting light that was a magnetized gas, for example, that would be affecting the spectral lines. So earlier on, I showed these peaks where we had one spectral line per element or per atomic transition. But what happens when you have a magnetic field is that the spectral line splits. So it can broaden, and in a strong field it can split. So for example, you might have a stationary component at the original wavelength, and then a component either side, one at a slightly shorter and one at a slightly longer wavelength. And this is now called the Zeeman effect, after Zeeman. And it's an amazing piece of research because it means we can detect magnetic fields from a distance. If something that's emitting light is also magnetized, there's a fingerprint of that in the light that it transmits to us. So that's the first piece of information. So I'm building now towards something that we learned about the sun. The second piece of information that actually was announced right here in 1897 by J.J. Thomson, who I've shown here, is the discovery of the electron, although it wasn't called the electron at the time. But subatomic negatively charged particles. So that's the next piece of information that I want us to keep in mind. A third piece of information is an experiment that was carried out by Henry Rowland. He did an experiment where he had an electrically charged disk and he rotated it and realized that it created a magnetic field. So here again, we've got this link between electricity and magnetism, flow of electrically charged particles, and so on. So these three pieces of research come together to be relevant to our story of the sun because they were put together by this man. And this is George Ellery Hale. Maybe I could just have a show of hands if you've heard of George Ellery Hale before. Oh, yes, some people. Brilliant. I think he is the most important person in solar physics. I'm so glad that he's a name that's familiar to some people in here. If he's not, by the end of tonight, he will be. He'll be someone that you'll be thinking about. He was an amazing American astronomer/engineer. He came from a wealthy family. He had a very high-quality observatory, even as a child, that his father funded for him. But he had an amazing mind where he was able to bring together different areas of science and synthesize them together to make new discoveries. So he knew about electrons, he knew about rotating charged disks creating magnetic fields, and he knew that you could detect a magnetic field from a distance. And actually, Zeeman was also, of course, aware of this. And Zeeman was thinking, well, if the sun has a magnetic field, what I've discovered would enable us to detect it. But it takes more than that. You have to know information about the sun as well. And George Ellery Hale had become very proficient at building instrumentation to study the sun. In particular, the developments around spectroscopy and light and his engineering led him to build a telescope that looked at very particular wavelengths of the light that the sun gives off. So not the whole visible light spectrum, but different or particular wavelengths. And in the early 1900s, in 1908 in fact, he built a telescope that could pick up light from the sun in the wavelength of what we call hydrogen alpha. So this is light created by a particular energy transition as an electron falls to a lower energy level in your hydrogen and gives off light. And we call it hydrogen alpha. And it's a really important line for observing the sun even today. And this is the image that he created. So this is now looking not at the photosphere of the sun, not at that visible surface, also not at the corona high up, but at a layer in the middle that we call the chromosphere. And you see a huge amount of structure. You can probably just about see some sunspots on the top right and one down right in the center in the bottom. And then also this snake-like feature that we call a filament in the sun's atmosphere. And Hale noticed something curious about the shapes in the sun's plasma. So he knew by this time that the sun was hot gas. So the elements, the atoms would be torn apart. So he thought probably, yes, there are electrons freely floating in the atmosphere of the sun that have been torn away from their atoms. And he noticed something else. And I'm going to show you a modern image now to illustrate something that caught Hale's eye. So this is a modern image of the sun taken in the light of hydrogen alpha. This is actually an image taken back in April this year. So April this year, when we had an enormous sunspot crossing the surface of the sun. And I don't know if anyone in this room went out and saw it. Yes, you saw it. Did you have Eclipse viewers?
Photographed it as well.
Brilliant. Have you got that photo with you? Oh, I see it later. That'd be brilliant. So this is an amazing event. So we get so excited. Large sunspot appeared on the sun, and it was visible to the naked eye if you had filters. So we all went outside and put on our Eclipse viewers and looked at this sunspot. It was amazing. And it was interesting. So I had a new PhD student at the time, and he was saying, I can't see it. And I was like, right, I need to train you a bit more. So next time this happens, he will be able to see it. So this is the sun in hydrogen alpha. This is the visible light image just to show you that sunspot. It's absolutely ginormous. For size, as a context, you'd fit 110 Earths across the width of the sun. So this is many times the size of the Earth. This sunspot, absolutely enormous. But this is at the same time in the light of hydrogen alpha, just picking out a narrow spectral range. And then if I zoom into that sunspot region, hopefully what you'll see is that you've got the dark sunspot, but you've got these sort of spiral, like Catherine wheel sort of features around the sunspots. And Hale called these solar vortices. So he was looking at the sun thinking, okay, there's probably electrons here. There's some sort of vortical motion, and vortical motion of something charged can create a magnetic field. And if it creates a magnetic field, I know how to detect it because of the Zeeman effect of splitting of the spectral lines. And he knew how to test that because he was an amazing instrument maker. And so in 1908, George Ellery Hale became the person who had put all this information together, built the right telescope, looked at sunspot regions, and detected that they were indeed sources of strong magnetic field. So the first discovery of a magnetic field beyond the Earth, and I would say the point when solar physics really began. So 300 years after the first telescopic observations of sunspots, we finally knew they are sources of strong magnetic field. So when we look at images like this today, we know that they're magnetic field regions, and they're regions where plasma, electrically charged gas, is trapped and is able to cool down slightly relative to the surrounding photosphere. So the magnetic field and the strength of it is what creates these dark spots on the surface of the sun. And this discovery was so important. And it found an advocate here at the RI in Arthur Eddington, who was a mathematician and astronomer and very famous scientist working at Cambridge. He was the person who also supported Einstein's general theory of relativity, went on an eclipse expedition in 1919 to measure deflection of starlight during a solar eclipse and looked at or backed up the idea, backed up Einstein's theories. But anyway, that's another story. So in 1909, Eddington was giving a Friday evening discourse, and he was supposed to be talking about, or was talking about, the moons of Saturn, how many had been discovered. I forget, it's a tiny number compared to the, 60-odd or whatever it is we know today. So he was talking about the moons of Saturn and comets. But I love the fact that he ends his Friday evening discourse. And again, these are all here in the archive. Some of them are online as well, so you can read these. And he says, I cannot close this discourse without alluding to what is perhaps the greatest result of any that recent years have afforded to astronomy. And he talks about Hale. He has gone farther and shown, I believe, to the satisfaction of physicists, that the light passing up through these vortices bears the sure marks of having passed through a strong magnetic field. This work was so important, Eddington couldn't resist on this spot talking about it. And shortly after, George Ellery Hale was invited here to give his Friday evening discourse, and then also because of the significance of his work was invited to become a member of the RI. So his work was absolutely fundamentally important to us in solar physics, even to this day. So the sun is not only a very dynamic ball of plasma, but it's a magnetized ball of plasma. And so that's how I want to finish off in the last section of my talk, the last few slides. So my job today heavily revolves around measuring and using magnetic field data of the sun. So the kind of images that I would use are like this. So this is now a magnetic map of the surface of the sun. It shows us regions where the magnetic field points out of the visible surface, and that's shown in white. Then regions where it points in black. So that's like having a north and south pole on the surface of the sun. And there will be magnetic field going from one pole to the other. Now, of course, I can't get to the sun and sprinkle my iron filings, but what I can do is make use of this data, the strength and direction of the magnetic field, and then the physics of magnetic fields to create what we would call an extrapolation, illustrated here using the concept of magnetic field lines as introduced by Michael Faraday. So here you can see between the black and the white giant arches of magnetic field stretching out far into the atmosphere of the sun. So you cannot study the sun without thinking about or knowing and studying its magnetic fields. And as those sunspots change over time with new ones forming, old ones dying, so the magnetic field in the atmosphere of the sun and threading the surface evolves. It is a dynamic object. But once we knew about magnetic fields, we could start to understand the forms of solar activity. So the solar flares that I mentioned are interpreted as being releases of energy stored in magnetic fields in the sun's atmosphere, releases of magnetic energy, an energy that's then converted into other forms, particle acceleration and radiation. But for the form of activity that I'm most interested in, which are these coronal mass ejections, I want to show you that in a bit more detail. So this is an illustration of one quite small coronal mass ejection that happened on the sun. On the top left-hand side is an image of the sun in soft X-rays. So this is glowing hot plasma, a few million Kelvin. And then on the right-hand side in green is an ultraviolet light movie of the sunspot region that produced the coronal mass ejection. So if I run that movie, you'll see there's a little tiny flare that happens, but the magnetic field in that region reconfigures. And okay, we can't see directly the magnetic field now, but what we can see are the shapes in the plasma. And there's a really nice relationship between a magnetic field and a plasma, which is electrically charged, in that the electrically charged plasma gets trapped in the magnetic field and it traces out its shapes in a sort of an analogous way to having iron filings. So I can look at the shapes in the magnetic field, shapes in the plasma emission, and use that to learn something about what the magnetic field is doing. So if I just run that again, you'll see that when the configuration changes, that's a change in the magnetic field. And you may also have seen a wave that comes out from that eruption as well. I'll just play it again. Does it show? Oops, is it going to play? Yeah, boom, this wave. And that's because of the expansion of this eruption. When we look at it in artificial eclipse data, so this is artificial eclipse, this is not a particularly clear movie, but you can see that material being ejected away from the sun. But we wanted to understand, we do want to understand, and this is a worldwide effort, why does the sun suddenly erupt the mass of a mountain into the solar system at speeds of up to a few thousand kilometers a second? And in the same way that we think the energy that powers solar flares comes from the magnetic field, we also think that for these coronal mass ejections. That the sun's magnetic field is dynamic, it evolves, and it stores up free energy. But that's not enough. And a lot of the focus in recent years on understanding coronal mass ejections has been around what shapes the magnetic field takes on. So what I want to show you now is a series of images of this little region of magnetic field and plasma and how it changes over a couple of days. So here on the bottom, that's zoomed in now, and over a couple of days, so imagine you're looking down on this part of the sun. I want you to try and visualize, well, if I had an arched magnetic field with gas running along it, I would see some straight features. And that's how I interpret what we have on the left-hand side, a series of arches viewed from above. But as time goes on, over a couple of days, this whole magnetic field structure and the plasma trapped in it changes to become something that looks like an S shape. And that, I think, not all my colleagues agree, but is a signal that the magnetic field is evolving into something that we call a flux rope. So this is now, if you imagine your bundle of magnetic field lines, if I twisted them, I could make a helix or a helical shape. And a flux rope is a magnetic field configuration where the field lines are helical. And so the work that we've been doing at UCL and with collaborators is looking at the formation of helical structures in the sun's atmosphere. And we've also done modelling. This is modelling work done by Antonia Savcheva, who works in the US. And so within her computer, she again uses the physics of magnetic fields and is able to create a magnetic flux rope that we can then compare directly to the observations. So in her magnetic field line models, do we see the same shapes in the plasma emission in the sun's atmosphere? And I would argue that we do. They go from being more like a series of arches into being something that's S-shaped. So a lot of the work that we've done now around coronal mass ejections has been about the identification of flux ropes in the sun's atmosphere. And so I think this is perhaps my last slide now to illustrate why we care about flux ropes. Why should we care? Well, there's a good reason. Because if you build a flux rope in the sun's atmosphere, it has a very good chance of being able to expand upwards very quickly. And that could be the cause of the coronal mass ejection. So I've got a couple of simulations to show you to illustrate what I mean. So these are the two simulations. First of all, I'm going to play the one on the top left. And what I want you to notice, though, is that rainbow-coloured helical structure. That's the flux rope in the sun's atmosphere. Well, okay, in my colleague's computer. But anyway, simulating what's happening in the sun's atmosphere. Above it are the magnetic arches in the sun's atmosphere. But my colleague can evolve this configuration and he can make it undergo an eruption. So there you see it rising up and escaping the sun. So magnetic flux ropes are very interesting structures. And they can undergo a magnetic instability once they've formed. That means actually we can get them to erupt at very high speeds to escape the sun. Then just to show you this other one, so this I really like, I find this quite compelling. So this one now you see the twisted helical structure of the magnetic flux rope. Rising up, this time it's undergoing something that we call the helical kink instability. So as well as rising, it twists, and you see it kinking. So on the right-hand side, you've got the simulation, and on the left-hand side, you've got the solar observations of the origins of an eruption. And you can see how closely they match together. So there's a lot of work now in using magnetic field structures to explain coronal mass ejections. Okay, I think I've probably filled my time, so I just have one last slide. So I couldn't finish the talk without at least mentioning that, okay, we can look at the visible surface of the sun, we can look at the atmosphere of the sun, we can look at the atmosphere out towards the earth and beyond, but we can also look inside the sun. So this last visualization makes use of the fact that we can probe the solar interior, where the fusion is happening to generate sunlight in the first place, and also where the magnetic field of the sun is originating. So as this movie plays, you'll see the sun spinning, and then it will open up and show us the inside of the sun. We use the technique of helioseismology to probe inside. It's a technique of using sound waves measured at the surface of the sun to look inside. The sound waves pass through the sun, pick up information about the interior layers, and then we collect it at the surface. So this is a NASA visualization that shows the outer layers of the sun. And all the lines you can see are magnetic field lines. And you'll see that they evolve over time. They become tightly packed together, and then they die away. And then they become tightly packed together, and they die away. On the right-hand side, you can also see the number of sunspots varying over time. In blue and red, you have the interior flows being indicated. And then on the left-hand side, the blue and yellow is the strength of the magnetic field inside the sun. So we see sunspots at the surface, but they begin their life as magnetic fields that get amplified inside the sun. Incredible. And actually, the origin of this work that we call the solar dynamo, the transformation of rotational energy of the sun into magnetic energy, that was carried out at Mount Wilson, which is one of the observatories that George Ellery Hale was absolutely key in. So many things track back to Hale. So I think I should probably finish on that point, but I want to say I hope that that's given you a flavour of the amount of time it's taken to come to understand something as simple as a sunspot, several hundred years, but that our modern view of the sun is that it's dynamic, it's variable, but it also has an impact on us here on the earth. So I think I would say thank you for listening, and I can take any questions.